Action.
Hello, my dear students, and welcome to the laboratory discussion portion of our Woosh bottle experiment. In this Woosh bottle experiment, it's a classic chemical demonstration experiment because it's impressive, involves lots of shooting flame out of bottles. You can do this at home. You don't have to use 100% isopropyl alcohol. You can use other alcohols. Do not use methanol. The reaction would be too violent and potentially break the glass. But in this reaction, you saw the following. Now, the first question says, what happened in the demonstration? And what we did was we took 20 milliliters of isopropyl alcohol, 91% isopropyl alcohol, but we won't make a correction for that, not being 100%. And we added it to a 20-liter carboy, and we put it on its side, back and forth, to coat the sides of the carboy and to saturate the atmosphere with the isopropanol, which it basically evaporated and did entirely, because when we turned it all the way upside down, none of it dripped out again. Then we took a lighter, we ignited the alcohol. The alcohol ignited, burned, combusted, combined with oxygen to form carbon dioxide and water, producing a tremendous flame and a whoosh sound as the gases moved in and out of the narrow opening of the bottle. Then we tilted the bottle upside down. Well, we let the water pool at the bottom, and then we tilted it upside down and measured our water produced in the reaction. The second question says, write a balanced chemical equation for the combustion of isopropyl alcohol. Isopropyl alcohol is a 3-carbon alcohol. It's 3 carbons, 8 hydrogens, and 1 oxygen. The alcoholic OH group has 2 possible positions it can go to. It can go on the end, and that makes it N-propanol or normal propanol. Or it can go on the middle carbon. And when you do that, that's why we call it isopropanol. The iso stands for isomer or isomeric. Iso means other and mer means body. So it's another different body or a different form of this chemical, even though it has the same chemical formula, C3H8O. Now, it says write a balanced chemical equation. I've gone ahead and done it in advance for you. If you take 2 molecules of isopropanol, 9 moles or 9 molecules of oxygen, you will produce 6 molecules or 6 moles of carbon dioxide plus 8 moles or 8 molecules of water, depending on what units you're going to use. So 2 of these plus 9 of these produce 6 of these plus 8 of these. Okay? Now our next question says, calculate the volume of water you would expect to be produced by this reaction using the equation above. So we would expect that for every 2 of these, we would produce 8 of these. But the question is, we need to convert it to moles. So if you look at the formula mass weight of formula mass or molecular weight, molecular mass of isopropanol, there's 3 carbons, they're 12 each, 12.0017 or something. There are 8 hydrogens, which are 1.00 something, but 1 for a total of 8. The 3 carbons give us a total of 36, and there's 1 oxygen of 16 or 15.999 something. So we'll call that 16 for a total molar mass of 60 grams per mole. Now, we had 20 milliliters of isopropanol. It's less dense than water, it's 0.78 grams per milliliter. So we added even though we added 20 milliliters, we only added 15.6 grams. My milliliters cancel for my density value of 0.78 and gives me 15.6 grams. Well, I use my mole map. And here's my mole map. And to convert between grams and moles, you follow your mole map. It says divide by the molar mass. The molar mass is 60. We're trying to zoom in on that mole map. So, you just do what it says. It says grams here. We want to convert to moles. We know we have 15.6 grams. So we divide by our molar mass, which we just calculated, and that gives me 0.26 moles. Now, how many moles of isopropanol? We used in the experiment 0.26 moles of isopropanol. Now, how many moles of water are we going to produce? Well, in the reaction, every 2 moles of isopropanol produce 8 moles of water. So I set up my mole ratio. That's a ratio of 2 to 8. 2 moles of isopropanol to 8 moles of water. But we didn't have 2 moles, we had 0.26 moles. And the question is, how much water should I produce? So if you set up this mole ratio and then cross multiply, 2x is equal to 8 times 0.26. So I divided both sides by 2, and 8 divided by 2 is 4. And 4 times 0.26 is 1.04. So I should have, from this many moles of isopropanol, produced this many moles of water. About 4 times as much, 1.04 moles. But when we measured the water, there were 10 milliliters. Now, water is pretty convenient because it has a density of 1 gram per 1 ml. So 10 milliliters is equal to 10 grams. Water, H2O, oxygen 16, each hydrogen is 1. So water has a density of 18 grams per mil. So again, if I want to convert my 10 grams of water to number of moles of water, I follow my mole map. It says divide by the molar mass, the molecular weight, the molecular mass, and that is 18 grams, 1 mole per 18 grams. So I'm dividing 10 by 18, and I get 0.55555 with significant figures, 0.56 moles. So now the question we need to answer is, and you're showing your work here, is calculate the volume of water you would have expected to be produced. And I'm also asking you now to calculate your percent yield. Our percent yield is equal to the actual number of moles divided by the expected. We expected 0.56. Okay? I'm sorry. We expected 1.04 over here. And we produced 0.56. So now, if I do a quick calculation, I'll see that my yield is just a little bit over 50%. So 0.56 divided by 1.04 times 100% is equal to 0.538461538. Don't give me that. Keep significant figures. And this would be, my fraction would be 0.54. But of course, this is a percent, so we multiply it by 100. So my percentage would be 54%. 538. And that's my yield. Where'd the extra water go? And, we still didn't actually calculate the volume of water you would expect. We expected, 1.04 moles and of water, and at 18 grams per mole, that would equal to approximately 18 milliliters. Is the answer to that question. The answer to my question, which is, what is the percent yield, is 54%. So, a very simple experiment measuring volumes of propanol used and water produced gives us the ability to make some very sophisticated calculations. So finally it asks, why does this reaction occur so fast? And it occurs so fast in the vapor phase because when it's not actually liquid alcohol that burns. It's the molecules vaporizing and leaving the alcohol. Only the surface of the alcohol can burn. The molecules down below can't because they're shielded from the oxygen by the molecules above the surface. But when you expand those molecules out into a vapor, surround them with oxygen molecules in the air, remember the air is 20% oxygen, then you have a perfect storm. You have a greater surface area, and those molecules can react and burn very quickly. So there's your answers. There's your explanation of what happened and your calculations that are expected for this reaction. So we will post, we've jumped ahead because I still need to get a video done of our limiting reagent lab where we dissolve the magnesium in the acid. We'll post that video next, hopefully tomorrow. Until then, stay safe and goodbye.